This UCSD TV program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest programs.
I'd like to welcome you all to the first of the two climate change sessions. This one, it's all free form. In fact, I have no idea what the other people in my section are going to talk about, but we'll find out soon. The descriptor is drivers and mitigation, and I'm Ray Weiss. I'm a geochemist here at SIO. Who started working in the ocean and using chemical tracers to study ocean circulation and gradually evolved into the atmosphere in kind of a Darwinian fashion, and that's most of what I do now. The other speakers here are geochemists as well. I'm going to go last. Mark Thiemens, who is a chemist, geochemist, and our Dean of Physical Sciences here at UCSD, will be the first speaker, and he will tell you what he's going to talk about.
Thank you, Ray, I guess. So I'll have to decide as I go along what I'm going to do. So I've got some slides in here. I'll stick on time. But I wanted to say happy birthday to Charlie. So what do you say? First of all, well, I was on a search committee that hired Charlie, and also the search committee that hired Margaret, for that matter. And when we were going through and learning about the director of Scripps, one of the things that I thought was cool was that the Scripps number of ships puts it in the range of some of the navies of the world. So I thought when I got to know Charlie that I would change his name, and that's why I call him Admiral Kennel. Now the thing is, for the Admiral, nobody's talked about a birthday present. All right, well, let's talk about birthday presents. So what am I going to get for him? I got to get something for Charlie. It's got to be something different. So I thought of something. And I thought of it like in the middle of the night. So, oh, I didn't think of this. This is perfect. It's a gift. And I remember that I'd ordered it a long time ago. I got it in person. It hasn't been delivered yet, but I have a picture of it. So you have to get something that's really appropriate for the man. This man's famous. Everyone knows him. And it's a gift. It's not a unique idea. I admit, it's not a unique idea. It's been done before. So I can't take credit for the idea. It's a secondhand idea. But nonetheless, it's on the way, Charlie. But camels just aren't what they used to be. Every time I go to the place, I'm telling you, I get ripped off. I get slow camels. They bite and they spit. I mean, besides monkeys are the two animals I like the least. So it's on the way, Charlie, and happy birthday. Now, I work on isotopes, and I do two things in this regard. One is what I did in my first job here, in my first part of my job, is I was hired as a replacement for Hans Suess, who some of you know, and I took over the laboratory of Harold Urey, who some of you know also. And that's why I have this. It has hydrogen, deuterium, and tritium, which Urey was responsible for. And part of it is that we measure these things, but we do the basic physical chemistry. And my first experiment here found a new law in physical chemistry and isotope effects. And it turned out that it was really a mess in terms of the chemical dynamics, and we've made a living with that and other things. But the most important part is that it's a weird thing. And that's what I'll mostly talk about, is the forensics. We go out and measure this, and part of the deal is we have to develop abilities to measure things in different things, and small and precise. So part of it is understanding new rules. So when I came here, I was in Mayer Hall. In fact, where's Bob Dines? I was going to say, I was in Mayer Hall when I first came here. Now I'm in Urey Hall, which is probably where I belong. But I flooded Bob Dines' laboratory, and a physicist kicked me out of Mayer Hall. And so I've been banished to Urey Hall ever since. And so, but it's okay, it's appropriate. Now, in keeping with the Israel theme, part of what we do is try to understand, I'm just going to show to make the case, and understanding these rules, what's in it. And part of it is just pure, honest to God, quantum mechanics. And I wrote a theoretical paper with a guy in a PNAS, with a guy, and so keeping on this theme of Israel, Raphael Levine, who's a quantum chemist in Hebrew University, trying to understand the dynamics of what happens in selection when you break a bond. Seems simple, but you have to take a molecule where you know everything, and this is one here, nitrogen. You have covalent states, you have Rydberg states, you have interaction states, and you have to calculate everything from first principles. We did. Then after you do that, and this is a paper, and then after you do that, you have to worry about that part, then you have to allow them to interact and perturb each other. So you have to solve the transition dipole moments, you have to do the diabatic part, and then you have to do the time-dependent Schrodinger equation to break it apart. And you can do that, and we did that. Now we've measured it in carbon monoxide because astrophysically, which is where I'm going to go with this, that's really important. There's a lot of you in this audience, you know, if you do look at the radio astronomy and interstellar molecular clouds, carbon monoxide is important. If you're going to make planets out of oxygen, which is what I want to do, you got to understand carbon monoxide, period. That's just it. Planets are 50-some-odd% oxygen, and before that, it's all in carbon monoxide, so you have to understand it. So we measured it and published a paper in Science on it. Yesterday, a paper got accepted for following up on the calculations in nitrogen, got accepted in the proceedings in National Academy of Sciences. So part of what we do is this. I'm not going to talk about it anymore because you'll fall asleep if I talk about real chemistry. This is a good way to have people leave you alone on an airplane. You sit down on an airplane, you want to read. What do? I'm a chemist. That's it. They're good for 15 hours, and even if they get really bored, they still won't talk to you. And this is where we did the experiments. This is the advanced light synchrotron in the Republic of Berkeley. And so we did the experiments here, and it's a nice thing. So part of what I'm going to talk about, this is a special edition I wrote on cosmochemistry. I was hired as a cosmochemist. What do you do as a cosmochemist? Yuri invented this field, and it started in the 40s. You understand the origin, distribution of the elements, which is where I came at this, which is from stellar nucleosynthesis, through the planets and distribution all the way through until the origin and evolution of life. And then once you have a planet, then the cosmochemists don't care and they turn it over to the other people. So that's what I was hired to do. And this is a picture of me in my early sampling days on the moon. So what we're trying to do is try to go from this phase here, which is what I'm talking about, is when it's still in a planetary pre-solar nebula and the sun is just turning on, doing photochemistry, making molecules, all the way through making planets into here where you get into a meteorite. A lot of what we do is meteorite work also. So at that stage, here's what it is. I worked at I came here from the Fermi Institute at the University of Chicago. I worked with people there that studied oxygen isotopes in meteorites. And there's this funny isotope distribution that you see in meteorites. The theory for this oxygen isotope distribution, that this is supernova debris. This was the theory for 20 years, is that you had a supernova, explosive carbon burning, you give off pure oxygen-16, which is what's showing in this plot, and that triggers the formation of the solar system. And Al Kaminer and a lot of people had models for doing this. Aluminum-26 gave you the time scale for doing this, and it worked well. But it's all based on one theory, that the only way you can get this is a nuclear process. So the first experiment I did with my startup money of $250 here at UCSD was to show that you can do the same experiment in the formation of a simple molecule that's exactly the same in the meteorite. We immediately ruled out supernova debris in our experiments. Messy as our laboratories are, there's some doubt about this. But to show that you can do this chemically. The trick has been to work out the quantum chemistry of this effect. It's turned out to be really difficult. There's 5 contenders. One by Rudy Marcus at Caltech, who's a Nobel laureate, and he's been working on it for 12 years. And his theory's probably wrong. Or people don't agree with it. It may be right, but most of the other chemical physicists don't agree with it. The trick, to me, has always been, can I convince the meteorite people and the planetary geochemists that you can do this? And so we had to do an experiment where, and we just did this and reported it last year, where you get the same effect in making a solid from a gas. Exactly the same. So the gas to particle solid formation process is where you get the isotope effect that you see here. So that's the first step in going from a gas to a planet. No one's ever worked this out. So we did it experimentally, but I won't go into the details of this, but basically, this process is important in climate. How do you actually make a solid particle? No one knows the real quantum chemical level of how you do that. You need to know that for the climate studies, but you need to know it for the solar system. It's a nano question that's a problem. And so all of these, we just published this year. This is a paper in PNAS. This actually is me on the cover. I told my friends, I made the cover of PNAS. That actually is me at the South Pole. And part of this comes into trying to understand the climate forcing aerosol issue and trying to understand what goes on our particle surfaces. So this is a paper that my colleague Rabina Shaheen wrote. It was 2010, but it was a great paper, and it was a paper of the year actually in physical sciences in PNAS, to look at the nanolayer physics of what happens on these surfaces. And this is an important problem. We published another paper in trying to look at this with my colleague Dmitry Bazov in this year actually, using polaritons to map surfaces. And so this reports a new type of imaging to study these processes. And some of these ones we try to collect at the South Pole. This is a picture of me in my happy days at the bottom of a damn snow pit of 30 tons of digging to look at the climate record. And in another paper of this, what you can see in the sulfur isotope record, that you find anomalies in the snow pit that derive from the El Nino effect. And what happens in the El Nino effect is you get more heat in the equator that transports to the pole. We spotted it, Rabina spotted it, only because the 1998 El Nino was so big, it showed up in the South Pole. So when we back and looked in the years before, it turns out that the ITZZ has a big part in controlling this. But you only spot it first from the anomalous year of the El Nino. And so that's, part of that then is trying to understand what happens in transport along the way. This is from the ITZZ to the Antarctic, but at the same time, we're interested now in what happens from here across here. So part of what we're doing is trying to map out what's happening up here as it transports over to the east. And this is in the Tibetan Himalayas. This is now at 20,000 feet instead of 10,000. Same thing, damn snow pit. And then try to understand it. The same processes are relevant for Mars. If you want to work on Mars, you have to realize if you're going to work there, let me know ahead of time, it's dangerous. And we're trying to understand water on Mars. And part of it is the processes that occur on these mineral grains. And so part of this is the Mars missions in the future, and we work with the Martian meteorites using this effect to understand it. I'm out of time and I need to close up. But working in the Martian meteorites, looking at the water and the carbonates in this, and this is another science paper, what you see is that the water in the Martian regolith and the Martian rocks is not consistent with any of the theories of Mars formation, and especially what happens on the surface. So there's a lot of things that we want to work on with the Mars. The other part of it is the snowball Earth. This is an interesting one. This is to end up with the biology, so I can quit and go home. So the snowball Earth is interesting. The Earth, back when it was all put together in one piece, ended up by bad juju in the equator. And what happens is the water and excess heat weathers the planet. Well, how do you do that? Well, silicate plus carbon dioxide, it's known as the Uri reaction, in fact, sucks the carbon dioxide out of the atmosphere. What happens? It freezes. Geologists agree it's been frozen. And here's what's interesting. This is the mystery. Here's the oldest rocks on Earth, are about here. Here's the great oxygenation event. And then here's basically what you find for life. Algae, archaea, and whatnot. And then the Earth freezes solid for about 0.99 million years is the actual number. And then it unfreezes and everybody appears. It's true. You can look it up. It's in the fossils. And here it is in China. We went last year and this year actually also to this area to sample these snowball Earth samples. And this little carbonate layer is where all that happens. Down here, that's all the algae and fungi. Up here, everybody else appears. Nobody knows why. It's a great mystery. It's the origin and evolution of life. What happened here? So we're interested in that. So what's one of our best discoveries? One of the best discoveries was in moving here. It's the fish taco. Second best is looking at sulfur isotopes. And this is just, if you want to understand the origin and evolution of life, you have to understand where does the oxygen come from? When did it come in? How much was there? Where did it go? So from our work on Mars, we found this funny sulfur distribution. And we showed that it comes from SO2 photolysis. In today's atmosphere, it doesn't happen. And it's because we have an ozone layer. The UV light you need to get this funny anomalous. It happens on Mars, but not here. What we showed then is we said, well, what if there was no oxygen and ozone in the Earth's atmosphere? Okay, then you should get the effect. But that's a hard experiment to do. But what if in the early Earth you see this record that means there was no oxygen and ozone? And if it comes and goes, then you would see oxygen from life come and go. So we measured it. So this is the anomaly 3.8 billion years ago, and it's coming and going and coming and going. And probably a third of the audience knows that around at this time period is the great oxygenation event. The banded irons form, poof, oxygen's here. Ozone's here, zap, the effect goes away. Nobody knows what happened. This appears to be what they call whiffs of oxygen. Oxygen coming in and going. Possibly a breathing, so to speak, of life coming in and going. Nobody knows why. So that's what we're trying to work out, is this part and this part here to snowball. What's the relationship? And part of it means going at grains, looking at those surfaces, understanding the basic physical chemistry, learning enough that I can talk to people like we heard earlier this morning, what happened to life. So it's a little long, but it's a little bit of everything. It's what we do. We see this in another paper that was out very recently. The same record that we see at the snow pit actually is the same as the one we see there. So part of what we're seeing transported to the South Pole is the same sort of chemistry, possibly stratospheric, possibly related to volcanic. So the mystery gets harder. So, and we missed by a week. This was on last week's cover of the Proceedings of the National Academy of Sciences. So we're off by, timing's everything. It's like comedy. But this was last week's cover. And so this is it. This is important. So first of all, you have to be brave. You got to take that first big step. And so, all right, I'm going to have to be brave. And so this is my favorite. This shows this. So look at this guy. I mean, tell me, if this guy can do this, we can do anything, man. This is great. This guy here, well, I don't know much about elephant morphology. I say a guy, it may not be, but I don't want to know anyway. You can do this. So my last slide to finish on my Israel theme, it's a picture that I had taken of me at a cistern, actually in Masada, back to Israel. Now, Martin Rees talked yesterday about multiverses. All right, you guys are smarter than I am. You guys are theoreticians. I'm an experimentalist. So I'm approaching this in a different way with the time, multi-universes, distance, travel. So this is my first attempt at time and distance travel, beamed across. And as I always tell people when I show this, you'll be happy to know that I'm actually not here. This is being brought to you from one of my favorite cities in the whole world, Key West, Florida. So if you have any questions, you'll have to go find the little projection room, and then you can ask me then. So thank you. I'm sorry for going over a little bit.
Thank you, Mark. I see that I was justified in saying I didn't know what he was going to talk about. So the next speaker is my Scripps colleague, Ralph Keeling, and I don't know what he's going to talk about either, but I think it probably has to do with the carbon cycle and oxygen in the atmosphere. Am I guessing correctly?
Yeah, that's right.
And Ralph is a geochemist as well and has spent his life doing this kind of work. Thank you.
One of the words in the title of this session was mitigation. And we didn't hear much about that in the last talk, and I'm sad to say that you're not going to hear much about it in this talk either. But I, at the last minute, gave my talk this rather ambitious title. But I'll be giving a kind of a personal perspective on where we are in this great geophysical experiment. Now, the concept of the great geophysical experiment is attributed to our former director, Roger Revelle, who was describing the buildup of carbon dioxide and its effect. But as far as I know, he never used the term great geophysical experiment. He called it the large-scale geophysical experiment. And it's probably a good thing he didn't use great, because if he wanted to give it a value assessment, he probably would have called it an atrocious geophysical experiment. After all, we're dosing the atmosphere with CO2, causing the oceans to rise, changing the patterns of rainfall, affecting agricultural production. Really, the consequences are frightening. But Revelle wasn't too worried about that. He saw this as a scientific opportunity and figured the concerns of humanity were a few decades off in any case. But my own career is really more in that tradition of just trying to understand what's happening without really worrying too much about the consequences in the day-to-day operations. In fact, I have to confess that it's exciting. And we saw this, I think, in Lynn Talley's talk yesterday. She could see the Weddell Sea warming over a 3 or 4 year period. That was exciting. Well, we can see atmospheric CO2 rising every year, and that's also exciting. So it's urgent, it's important, but it's also a fantastic experiment that we didn't have to propose. Imagine proposing to dose the atmosphere with CO2 to see what would happen. We get to find out. So where are we in CO2 concentration? So how did I get into this? So my father measured CO2 starting back in 1958. I had an aversion to the field that kept me out of it for long enough, but not forever. So I find myself here trying to keep these records going over time. And I should say that a big part of why these records have continued here is because we've had strong leadership, including Charlie Kennel as director. I also want to mention someone who didn't get mentioned before, is Tom Collins, who played a key role in the director's office and really facilitating aspects of this. It takes a lot of effort by a lot of people over time, and we've really benefited here at Scripps from a supportive environment for doing this kinds of long-term work, which is not normal university work to do something that's this repetitive. It's a challenge. So we went over 400 parts per million at Mauna Loa very briefly last year, and this year we went over for an even longer period, showing up in the monthly. So we are well into this geophysical experiment. It didn't start at 315 in 1958. If you run back further in the past, as you can now with ice cores, you see that it started about 280 parts per million. So we're really about 100 years into this geophysical experiment. What have we learned? Well, a lot of things are changing. One thing we know, I should say, back up, the rise in carbon dioxide is principally driven by fossil fuel burning. But it's very evident if you just do a simple mass balance that the actual rise is less than the amount we emitted. So the question isn't, why is it rising? The question is, why isn't it rising less? And the answer is, of course, that some of the carbon dioxide is being taken out by the ocean and by the land. And the principal way that it's taken out in the ocean involves inorganic chemical reactions where CO2 can react with carbonate ions and form bicarbonate. And the ocean has a vast capacity for absorbing carbon dioxide. However, the rate at which it can get in there is limited by kinetic factors, how fast the water is moving and how fast the molecules move at the air-sea interface. So it doesn't really soak it all up. That's why it's rising. But at the same time, the land plants can play a role. And the notion that the land biosphere might soak up carbon dioxide really goes all the way back to Revelle and Seuss in the early 50s. After all, plants do respond to carbon dioxide by growing faster in principle, and they could potentially take up carbon dioxide. And one of the things we've learned over the last decade is that the land really is playing quite a substantial role here. And I think there was a lot of skepticism, kind of quiet skepticism about that. The physics here is really unstoppable. But the notion that the plants would do something as amazing as they're doing took a while to get ingrained, and I think it's really pretty solid. So here's what the budget actually looks like now. This is the present emissions of fossil fuel, and on top of that, actually, there's emission of carbon dioxide from land, directly from land use, where we till the soils and we decompose it and the CO2 goes out, or we slash the forests and they burn and they go up as CO2. So those are sources. And then we know the atmospheric rise, so this part we know. We can kind of estimate in a variety of ways how much carbon dioxide is going into the ocean. And we find this residual sink. Some other process on land is soaking up really quite a lot of carbon dioxide. And 20 years ago, this residual sink problem was called the missing sink. It really was a question as to whether it was on land or somewhere else. But that's pretty much settled. It's a residual sink. It's the sink after you account for the source from land use. And it's big. Now, moreover, it's actually grown with time. So that not only has the methods of quantifying it to show that it's there gotten stronger, but it's actually gotten bigger itself. It's doing something that's responding to climate change. It's one of those features of taking stock of what's changed. The land is changing. Now, you can actually run this as a time series. This is a little bit complicated. This is time running from 1750 to the present. And these are the different contributions to the CO2 source and sink. Here's fossil fuel burning increasing here year by year. Here's the recent upsurge from China emissions, for example. Here's the land use. The land use was important early from the clearing of land for agriculture. It stayed important, but it really hasn't grown like fossil fuel. And here are the various sink processes. And you can see what I want you to highlight here is the sink from on the land has continued to grow with time. Now, this is sometimes called a natural sink. But there's nothing natural about it. It didn't happen in the past. So the land biosphere is somehow responding very unnaturally compared to natural ecosystems. And one of the ways, of course, it can happen is the CO2 fertilization. And this leads to an interesting dichotomy between the oceans and land. We talk about CO2 fertilization on land. That sounds like a good thing, right? In the ocean, we talk about ocean acidification. That sounds like a bad thing. But in truth, the difference isn't that great. We're perturbing both systems in profound ways, and we don't really understand the consequences, and we should be worried about both. So where I want to go now is the question, we see this large role of the land in soaking up carbon. What about the oceans? We know the oceans are taking up carbon by this inorganic process, but what about life in the ocean? Where's life in the ocean in this story? Did it fall out? Why don't we see anything here? And one of the challenges is, from a large perspective, is that if you actually look at the Mauna Loa rise, you ask the question, where is the signature of the oceans in this? The answer is that it's all these wiggles year by year are pretty much caused by the land biosphere. That's the land sucking up carbon, taking it back. So the seasonal part is the land biosphere. There are other wiggles with time here. We now know most of that is driven by land plants. The signature of the ocean is just in the slowing of the overall rise. But we don't see much character. We don't see much structure coming from the ocean from this. And one way we can get a better handle on that is by looking at atmospheric oxygen. Now, I should back up and point out that one of the ways we know the land is soaking up carbon is from measurements of oxygen that was done by my group and now various other groups. And you can separate the land out by a simple process of noticing that this process in the ocean here of inorganic chemistry doesn't affect oxygen at all, whereas the uptake by land plants does affect oxygen. So if you measure the trend in oxygen over time and correct for the land, you can get the ocean uptake. And then, of course, by balancing the CO2 sources and sinks, you can calculate the land and the ocean. So you get a decomposition, and it very much supports those earlier. One of the reasons we know the land is soaking up carbon is this kind of balance. Here's an example of data. Another way we know that the land is doing something odd has to do with looking at these seasonal swings. So here's the Mauna Loa record here, now showed against several other records that are almost comparable in length. And if you look at this broken record with a gap in the late 60s at Barrow, you see something spectacular going on. The swings have increased by about 50% over this time scale. Now, these swings are mostly caused by the boreal forests. So something profound has changed with the metabolism of the boreal forests over this time frame in the direction of higher metabolic rates. And that's consistent with the fact that the land is soaking up carbon. It's not obvious how it's related to that in quantitative terms, but it's clearly in the same direction. So we see this dramatic evidence of changes occurring on land. I should point out that these kinds of changes were not seen and not reported by ecologists going up and looking at the land surface. So you can have a fleet of people out there studying the forest in all different ways, and you don't get this big picture emerging. Now, it's now true that people who count trees can say, yes, we think there's a sink on land, but that's a new achievement of the last couple years. So that way of actually doing accounting and learning about how the whole system is changing is very much lagging behind the impression you get by looking at the large picture from the atmosphere. So the land is doing these profound things. And where are we headed? Here's just a perspective on the high latitudes. This is what the Arctic North Slope looks like today. If you go back when the CO2 concentrations were last 400 parts per million, there were boreal forests all the way up to the Arctic Ocean. So this landscape looked like that. And it's not like we're going back to the Pliocene. We're changing the world in lots of ways that are different than it would ever been back then, but we're changing it by the same kind of magnitude. So there's no reason to think that we couldn't someday, in a century or two in the future, start to have landscapes that look like that in regions that now look like this today. So the land surface is going crazy. And we can see that in lots of ways. So I return to this question, what role does the ocean play besides the passive response to rising CO2? And actually the conventional wisdom is that the ocean plays a rather small role. It has this passive inorganic process taking up carbon dioxide. But I would point out that we do not have the same kind of ability to track changes in in ocean biology as we have for land biology. And that's because we see all these little wiggles that I mentioned before that are driven by the land biosphere. We have metrics, not just of the overall impact, but we have all this other structural information about how the land is changing. We don't see that. Now, why don't we see the oceans in this? It has to do with this same buffering mechanism. The ocean can basically, because of the inorganic chemistry, we're not looking directly at ocean biology. We're looking only at the biology as seen after it's exchanged with the atmosphere. And that kind of damps out a lot of the information. So it's possible we just don't have ability to track the ocean the same way we have to track the land. And there is a way to get further at that with oxygen, and it involves kind of a clever little ruse here. This is the same budget I showed before, but now I've put ocean biology in here as well. I left it off for simplicity. But what does ocean biology do? It takes in carbon dioxide, it produces oxygen, you have decomposition, causing things in the other direction. And those changes can induce changes in surface water concentrations that drive fluxes across the air-sea interface. So all this is potentially going on. And what we don't really know is how these kinds of processes are evolving with time, along with the rise in carbon dioxide. We see this changing, but we don't have a very good clue on how that's changing. Now, one thing you can do is you can actually, if you combine these records of oxygen and carbon dioxide, you can kind of add the two together, the sum of oxygen plus carbon dioxide. And it turns out that land plants can't change that very much. Because whenever they breathe in carbon dioxide, they breathe out about 1 molecule of oxygen. They keep the sum constant. So if you add the two up, you can cancel out the land. And if you also correct for the fossil fuel effect on the two, which is pretty well known, you can start to see the residual changes over here. And you can compare that to what you think the ocean should be taking up by this passive process to see if there's anything else going on. So we do have a window into this phenomenology from the atmosphere. And that's one of the things that we're trying to exploit more fully as we go forward. So this combination is something we call atmospheric potential oxygen. And here's the time series of atmospheric potential oxygen. What's it caused by? It's going down in part because of fossil fuel burning, which consumes a little bit more oxygen for every CO2 emitted, more than 1 to 1. That's why there's a decrease. And then there's also this uptake of carbon over here going on. But then there might be this thing going on, too. So we have to correct both of these to see what else is left over. And by the way, we see a seasonal cycle here. That's not the land. That's this breathing process right here. We can see the oceans breathing in atmospheric oxygen mainly. It's mostly an oxygen effect, not a carbon dioxide effect, because of the buffering chemistry I mentioned. So this is the breathing of the ocean showing up. Is that breathing changing with time? Are there other things changing with time? And now that's the same data now plotted taking the seasonal cycle out and combined to the global average. So this is this trend in atmospheric potential oxygen. And here's a curve here, this straight line here with uncertainty bars on it in gray. And it's showing the trend you'd expect from The fossil fuel effect I mentioned, just consuming oxygen and producing some CO2, but not exactly canceling. And then there's this ocean passive response to rising CO2. They're both added together here. And here's the trend we see in atmospheric potential oxygen. And for about the first 10 years, starting after 1991, it was trending off. It was a little slower than that. And then sometime around 2000, it picked up its rate, started going faster. Now, this is a signature of something going on in ocean biogeochemistry. And one thing curious about the timing here is that this is right about the time that the global warming slowed down. So this looks like it's a signature of the hiatus. You say, aha! So the oceans are changing in some significant way around 2000. We can see it in atmospheric oxygen. And I think that's true, but there's a puzzle. And the puzzle is that if the ocean is taking up more heat, you'd expect it to be giving up more oxygen and carbon dioxide. So it's exactly backwards. Doesn't mean that the ocean isn't taking up heat. It means we don't understand the system yet. So there's an interesting puzzle here. So this is sort of a direction of where we're headed. This is my last slide. Was that a warning from Ray? Was that, probably should have been. So one other direction we're going, just briefly, we're also measuring in our lab argon concentrations in air. Now, argon is an inert gas, and nitrogen, although it's involved in biology, in the atmosphere there's so much of it, it behaves like an inert gas. And it doesn't vary, neither of these gases change in their abundance very much, except because they can dissolve in the ocean, and more dissolves in cold water. So their abundance is tied to how cold or warm the ocean is. And as the oceans as a whole warm, they're degassed into the atmosphere, and you actually preferentially degas argon over nitrogen. So you'll actually this ratio of argon to nitrogen in the atmosphere should be slowly increasing in time as the oceans warm. And furthermore, the rate should be very much tied to changes in whole ocean heat content. Now, this is still under development. The reason this hasn't gone very far, and it's still hard, is that these changes in argon nitrogen are tiny. I didn't mention that the oxygen changes we measure are tiny. These are even tinier. And you have to worry about all sorts of little analytical artifacts that can interfere with it. But it's a very attractive method from one standpoint, and that is that if you think about what the Argo floats do, they're out there, we heard about this yesterday, measuring temperature all over the place. Well, one thing you want to measure from all that is a distillation of the whole ocean heat content. Well, one thing that can happen, and does happen in the ocean, is that the water sloshes. You can have warm water here and cold water here, and they can kind of swap places a little bit. Now, if you're measuring in any place, you see temperatures changing. But there was no change in heat content in that. That's just a slosh. So nothing happened outside of that slosh. But if you try to measure that with Argo, it's very easy to get an artifactual change in heat content because you do something called aliasing. You didn't actually measure everywhere. So Argo will always have an alias issue, even with the high coverage it has today. And the same would apply to acoustic tomography. This method, although it has many limitations, does not have that limitation because it is a true whole ocean integral. And you get the ocean without even putting a probe in the water. You simply look at what's going on in the whole atmosphere. It'd be sort of like the Mauna Loa record of ocean warming. It's a marvelous dream, and it's an unfulfilled promise of my career, I have to say. But we're still chipping away at it. We do have argon data. Here's our oxygen data, and here's an argon record. It's a bit noisy. We don't see much of a trend. There is a constraint on whole ocean heat content here. It's not really enough to make a contribution to the debate at this point. So. Anyway, so that's another direction we're heading, just pure raw analytics to try to look at the big picture. Anyway, so I should finish there. Well, I should first of all point out the measurements that we do are really a result of a large group of people, a mixture of students and postdoc, a very fertile group for developing methods and thinking about all this. So thank you very much.
All right, I'm going to shift gears because I took the mitigation seriously. And I'm going to talk a little bit about other gases in the atmosphere and what they're doing to the climate. But before I do that, I wanted to wish, first of all, to thank Ellen and Charlie for inviting me to participate in this, and particularly to wish Charlie a happy birthday. My interactions with Charlie have come mainly through the fact that I served as his associate dean for academic reviews and advancements over, I guess, the entire period of his directorship. And I learned from that something that is kind of a life lesson for me, and that is that it's possible to be a really decent human being and still deal with these difficult issues as people's careers and their advancements and shortcomings and kudos and all those things. And I think Charlie did a marvelous job of doing that. I assume he did that throughout his career, and he's a remarkable human being for it. So thank you, Charlie. Now, yes. Okay, as I get older, I get closer to worrying about what's going to happen to the place when I'm no longer here. And as Charlie pointed out in the previous talk, a lot of people aren't taking mitigation very seriously. So I thought I would talk a little bit about greenhouse gases in the atmosphere. One of the adages you hear is that you can't manage what you can't measure. I'm not sure it's completely true, but you hear it often. And I'm involved in a program to measure gases around the world, working closely with my colleague Ron Prinn at MIT. We run a program that basically measures all of the non-CO2 greenhouse gases. And those are relevant both to the Montreal Protocol and the Kyoto Protocol, the Montreal Protocol being the predecessor and kind of the template for how Kyoto tried to work. The problem was that we had an engineering solution to this, and we don't have an engineering solution yet to this. But at any rate, they have common involvement in the study of gases around the planet, but for somewhat different reasons. And of course, there also are many gases which are both ozone-depleting substances and greenhouse gases, the CFCs being most prominent among them. So in this program, which is called the Advanced Global Atmospheric Gases Experiment, or A-GAGE, we measure all of these gases. There are about 50 of them now. In fact, this table is not completely up to date. Together, they represent about 30–35% of the change we've impacted on the radiative forcing of the Earth's atmosphere, so that the 400 ppm threshold for CO2, if you add on the 100-year global warming potential, you add the impact of these gases, or you do the radiative forcing at present, you get up around 550 ppm, or perhaps a little higher. So it's important that we look at all of these things, even though it's also important to remember that CO2 is by far the most important gas in this problem. But one of the interesting things you can learn by measuring the non-CO2 gases is that they're a lot simpler, especially the totally anthropogenic ones, which are what I'm going to focus on here. These gases are emitted from limited sources, and they're all engaged in Kyoto reporting and trying to understand impact on the climate. And they're very potent as greenhouse gases. The most potent of them is sulfur hexafluoride, which per mass of emission to the atmosphere on a 100-year time horizon has almost 23,000 times the effect of the same mass of CO2 emitted. And this is a record of northern and southern hemisphere concentrations in the global atmosphere, with the northern hemisphere being a little bit higher than the southern hemisphere because that's where most of the people are and where most of the emissions are. The two hemispheres lag each other. That is, the southern hemisphere lags, in this case, the northern hemisphere by about a year and a half. So you can take those trends. The lifetime is extremely long. It's thousands of years, 3,000 and some years for sulfur hexafluoride. So it's very easy to turn the slope of these lines into an emission assessment, and that's what this black line is. And the interesting thing is that we're engaged as a planet. All of those countries that have signed the Rio Convention, which created the Framework Convention on Climate Change, are obliged to report their emissions. And this is going to be the kernel of what I'd like to talk about, that when you add up, when they report their emissions, the idea is that this is the quantity that will then try to be limited by legislation. But we find when we measure the atmosphere, just as Ralph was pointing out, that when you do top-down measurements and compare them to what you think was going on by looking at the ground, there are sometimes enormous disconnects. And there are very big ones here also. This is what the only countries that are required to report are the so-called Annex I countries, or the industrialized countries. Importantly, it doesn't include China, India, or Brazil. and a number of other countries. But still, you would think that they would be the lion's share of the emission of this gas, which is used in electrical distribution systems. But it turns out when you compare the emissions that we see in the atmosphere, the black curve, to what's being reported for only the Annex I countries, there's a discrepancy of about a factor of 4. And there's a consortium in the Netherlands that has been trying to correct these numbers. They come up with the Annex I countries because they're trying to reconcile the difference between what you see in the atmosphere and what's being reported. They claim the Annex I countries are emitting about twice as much as they're reporting. And then when you add everything together, you get these numbers. So I guess the main message here is this discrepancy in emissions and emissions reporting. Which is quite large. And the uptick here, the enormous uptick, is generally attributed to the developing part of the world, mainly to China. And in fact, you can model the spatial distribution of the SF6 increases based on that station map I showed you. And this has been done by Matt Rigby and colleagues. And when those models are done, they show that from 1995 onwards, so that's in this time frame, the European and West Coast emissions have decreased, and emissions have increased everywhere else, including the eastern US and, of course, Asia. And you can do the same thing with the gas. This is the longest-lived greenhouse gas in the protocol. It's carbon tetrafluoride. It has a somewhat less global warming potential, but it's still a big number. And I might point out, by the way, that the gases with big global warming potentials are ideal candidates for carbon emission trading because you can make more money by restricting the emissions of less stuff than if you're actually doing it with CO2. So we can do the same thing here. We can compare the northern and southern hemisphere. These are based on, we weren't able to make these measurements until recently. This is actually a graph of measurements made on archived air that's been stored, some of it by Dave Keeling. So we sort of canvassed the world for old air and make measurements and able to reconstruct these curves. The slope of the curve, you can see, decreases as you go over time, and indeed the emissions are decreasing, but there's a misconnect here also. This gas is produced both by the electronics industry and the aluminum industry. It's generally believed mainly by the aluminum industry as a byproduct of making aluminum electrolytically. And when people who do the bottom-up assessments of the emissions, this EDGAR consortium has done the global emissions of this gas, and they've also done the global aluminum emission. The global aluminum emissions have been done by an aluminum industry consortium, and they have included China in their estimates. So if you add the green curve and the yellow or mustard curve together, you get the red curve, and that should be the global emissions without any correction for first world and second world countries. It ought to include all the developing countries. This is what the emissions are actually determined to be based on atmospheric measurement changes. So there's a factor of 2 disconnect here as well. And it's not a surprise, by the way, that we tend to find that the actual emissions of these gases are greater than what's being reported. I'm going to try to run through this fairly quickly. These are measurements of carbon tetrafluoride, this long-lived gas. Its lifetime is 50,000 years in the atmosphere. So it's something that's going to be there as long as we're going to be around. And this is what the individual measurements with these automated instruments show at a station that's fairly ideally located on Jeju Island, south of the Korean Peninsula, using this instrumentation developed here at Scripps. And you can see that there are these big spikes, and then the lowest values are the background atmosphere when clean air reaches the station, which represents the background value in the northern hemisphere at that latitude. So the question is, can you deconvolve where all of these, where this stuff is coming from using models? Because if the goal is to make, is to figure out what to do about this problem, we're unfortunately organized by countries, not as a globe, and so we need to find out who's responsible for what, and that's one of the leading edge areas of work in this basically just a year or so of time to show in detail what these points look like. You can use an algorithm to separate out the baseline. Then you can actually determine which points come from which place. And here's an example of a very high value with an air transport model showing that here's where the station is and showing, going back in days, the air trajectory with some mixing. This is a three-dimensional trajectory model based on weather observations called FlexPart. And you can see in counting days along here how the air has traveled to reach this station at ground level. And you can see in this case that the air has come over the industrial part of China. There's another point, another elevated point where the air has come from Korea rather than from China. And the reason that's an interesting distinction, let's go back and you can now look at the whole record that I showed you first with these discrimination applied to it. You can try to identify where things come from. So it's possible to actually look at the ratios of the enhancement of one gas to another, and that's what these plots do. In this case, the aluminum production has a different ratio of production of emission of C2F6, another perfluorinated gas, than CF4, and this is the ratio that comes from Korea, Japan, and Taiwan, where there is no aluminum production. You see one ratio. This is a ratio that comes from a station near Australia in Tasmania, where there is no electronics industry, but there is aluminum production. You can see the slopes of these lines are different. So that's the core of how you're able to discriminate between the two industries. This is a paper just recently published in GRL. And I won't spend much time on it because we don't have much, but we can compare then the top-down and bottom-up curves. The aluminum industry assigns a fairly large error to their top-down emissions, and we have a somewhat lesser error, to their bottom-up emissions. We have a somewhat lesser error based on this methodology for the top-down measurements, and we can find differences to explain what's going on. And basically, the aluminum industry global emissions agree within what they've reported, but if you look more closely, you can see that in the recent time the emissions have increased, and this is attributed to emissions in China from enormous amount of aluminum production in China. The semiconductor industry, on the other hand, you can, again, the same comparison is made here between the bottom-up reporting for these is for the two gases. I neglected to say that. And you can compare those emissions over time. The semiconductor industry, the discrepancies are significant, especially in this time period. The emissions from this industry are very complicated and difficult to quantify because of the need for industrial secrecy in what these companies are doing. So I'm going to skip talking about HFC-23, except to show it to you very quickly. This is the same kind of curve. This is a gas that only we here at Scripps are able to measure. It's also used in the semiconductor industry. In fact, environmental prizes have been given for switching to this gas in the semiconductor industry. It's a source of fluorine for plasmas that are used to clean things when you make these very high-density electronic circuits. It's also used, somewhat ironically, in making thin-film solar panels. And it's a very potent greenhouse gas. A global warming potential of nearly 15,000, fairly long lifetime, 500 or 600 years. We can deduce the emissions based on the trends, again using archived samples, and these are the emissions we come up with. The reported numbers are much lower for this gas. I'm sorry, I'm talking about, that's what happens when I don't read. I'm talking about HCFC-23. So that is a byproduct of, I hope some of you are reading. HCFC-23 is a byproduct of the production of the refrigerant HFC-23 is a byproduct of HCFC-22 production. That's a refrigerant still used in the developing world. There are discrepancies here in the emissions, but the interesting thing is that this decrease has been shown to be the result of the clean development mechanism, where producers in China have burned this gas rather than emitting it. The clean development mechanism is less effective now, and the gas is beginning to to rise again. That's the message that this shows. And in fact, you can do an inversion based on measurements at these stations, and that inversion has identified sources in China that are colored in here according to emission strength, and the X's are added. The X's are added post priori. They are added or post calculation. They're added to show the locations of where the factories of HCFC 22 are actually located. So it's possible not only to diagnose where these things are coming from remote measurements, but also this is over a year of observations, but also possible to determine whether the clean development mechanism is being adhered to or not. Now is a very quick NF3 slide, and I'm going to skip to the last one because it's interesting. It shows that the emissions of NF3 continue to rise very rapidly. The independent estimates are much lower by a factor of 2 roughly, but the interesting thing is that the industry, in response to our being able to measure this gas, as I said, we're the only ones now who are able to measure it in this program called A-Gauge, the emissions or production ratio was actually improved dramatically as a result of industries trying to respond to this, to these changes. So this is my final slide, and that is that the way forward here, there are uncertainties in all of this stuff. I hope I've persuaded you that there are enormous uncertainties in trying to add up emissions. I'm not a psychologist. I'm not an industrial engineer, so we can all speculate about the reasons for these discrepancies. But the task for us is to try to find out how to improve the methods of assessing regional emissions in such a way that, that we can make a realistic attempt at regulating these emissions. And so the way to do that is belongs to the modelers and optimal estimation techniques. This shows you the cycle of how this is done, that measurements, parameters, and so forth go into a 3D model. They predict concentrations. You compare those with the actual measurements in order to refine the parameters and run this system around in the hopes of improving things. For many gases, we actually get a better assessment of what the emissions are by doing the atmospheric measurements than have been reported under the United Nations Framework Convention. So the final message is one I'm fond of. Regulating emissions without verification against actual accumulation in the atmosphere is like going on a diet without weighing oneself. Thank you. So I'd like to take the prerogative of taking just a few minutes out of the session to ask if anybody has any pressing questions for Mark or Ralph or me. Yes, Bob.
I don't know anything about the other industries you talked about, but I do know the semiconductor industry.
Yes.
So it is a powerful surrogate for all of your models. In terms of where semiconductors have been made over time. So even starting in the 60s, they were fundamentally made here, into the 70s and even into the 80s. Around when TSMC, Taiwan Semiconductor Manufacturing, was founded in the late 1980s, semiconductors started to be made abroad. And through the 90s, they were fundamentally being made dominantly in Taiwan, with the exception of wherever Intel built a fab, and to some degree Samsung. In 2000, they started shifting to mainland China in a very significant way. And so you can use that whole record as well as the gases that are being used. You commented about using CF4 for etching and cleaning. And you can then work backwards to see whether or not over those periods of time you could predict where things were coming from. Because in the 90s, they'd be coming from Taiwan. In the 80s, they'd be coming from the United States and Europe. And in the first decade of this century, they would be coming fundamentally from China and Korea. And so you can check all of that to make certain that everything is working. Have you done that? Do you think about it?
No, I have a simple answer to your question, Bob, and that is that doing this regional deconvolution of where emissions are coming from requires high-frequency measurements, and we don't have those, except very recently when all of the emissions were already mainly in East Asia. That's because without those little spikes that are generated, if you do the global average, it's impossible to tell where things are coming from. We don't have the data density to do that, but we will going forward. So we'll see what happens if it's ever to leave Asia. But also there are issues between the different countries in Asia, as you know. So anything else? Thank you. Yes, one more. And then thank you for your patience. I know we ran over.
I had a question for you, Ralph. You talked about the oxygen in the atmosphere, the changes, and the potential of the mining changes on land. And I was wondering if there's a few changes that have occurred in the ocean, so I'm wondering if flooding is involved. For example, the increases in the eutrophication of coastal zones, the creation of dead zones, obviously that I would think that would have some impact on the oxygen. And also, there's a paper recently showing that oxygen in the oceans, particularly, is declining much everywhere. And so, again, want to how that factors into
Yeah, great question. There's a large body of measurements in the ocean that do show changes. So just in clarification of my point, it's not clear that those add up to making much difference to the CO2 budget. That's but I'm not sure how well that's constrained. So that's still true. Nevertheless, one of the concerns that has gotten more attention in the last decade or so of rising CO2 and climate change is loss of oxygen in the ocean interior. And this was first predicted more or less by models and it's simple to understand. Warm water will contain less oxygen because it's less soluble. Also, if you warm the ocean from above, which is what we're doing, you create a more stagnant ocean interior that will, over time, lose oxygen, and the balance ends up in the air, actually. So both of those things were expected from theory, and what's playing out isn't all that clear yet because the data is sort of sketchy. The measurements were not made with the idea of tracking changes over time, so people are trying to piece together trends from very incomplete and not necessarily adequate data. But the models did not predict the loss of oxygen in the tropics, and that's where it's being shown, for example. So I don't think we don't really know what's going on. I mean, the consequences for fisheries are, you probably could comment a lot more about that than I, but they're clearly significant. You have a contraction habitat if the fish can't dive as deep because they get into water where they effectively can't breathe. So we are kind of leading to a larger zone of the ocean where animals will suffocate. And that seems to be happening, and it was predicted by theory. So we have ocean acidification, we also have ocean deoxygenation. And that has some effect on what I do because, as I said, the balance of this loss in the ocean ends up in the air, so it has to be part of our accounting. And we do account for it, but it's more or less guesswork now. We want to do better. Hope that helped.
Okay. Thank you very much. I think Ellen has a couple, or friend. It's out of this session. Okay. Well, and I thank you. Okay, I thank you very much, and we'll go on to the next section.
Everything, and this is one here, nitrogen. You have covalent states, you have Rydberg states, you have interaction states, and you have to calculate everything from first principles. We did. Then after you do that, and this is a paper, and then after you do that, you have to worry about that part. Then you have to allow them to interact and perturb each other. So you have to solve the transition dipole moments, you have to do the diabatic part, and then you have to do the time-dependent Schrodinger equation to break it apart. And you can do that, and we did that. Now, we've measured it in carbon monoxide because astrophysically, which is where I'm going to go with this, that's really important. There's a lot of you in this audience. You know, if you do look at the radio astronomy and interstellar molecular clouds, carbon monoxide is important. If you're going to make planets out of oxygen, which is what I want to do, you got to understand carbon monoxide, period. That's just it. Planets are 50-some-odd% oxygen, and before that, it's all in carbon monoxide, so you have to understand it. So we measured it and published a paper in Science on it. Yesterday, a paper got accepted for following up on the calculations in nitrogen, got accepted in the proceedings in National Academy of Sciences. So part of what we do is this. I'm not going to talk about it anymore because you'll fall asleep if I talk about real chemistry. This is a good way to have people leave you alone on an airplane. You sit down on an airplane, you want to read. What do? I'm a chemist. That's it. They're good for 15 hours, and even if they get really bored, they still won't talk to you. And this is where we did the experiments. This is the advanced light synchrotron in the Republic of Berkeley. And so we did the experiments here, and it's a nice thing. So part of what I'm going to talk about, this is a special edition I wrote on cosmochemistry. I was also the search committee that hired Margaret, for that matter. And when we were going through and learning about the director of Scripps, one of the things that I thought was cool was that the Scripps number of ships puts it in the range of some of the navies of the world. So I thought when I got to know Charlie that I would change his name, and that's why I call him Admiral Kennel. Now the thing is, for the Admiral, nobody's talked about a birthday present. All right, well, let's talk about birthday presents. So what am I going to get for him? I got to get something for Charlie. It's got to be something different. So I thought of something. And I thought of it like in the middle of the night. So, oh, I didn't think of this. This is perfect. It's a gift. And I remember that I'd ordered it a long time ago. I got it in person. It hasn't been delivered yet, but I have a picture of it. So you have to get something that's really appropriate for the man. This man's famous. Everyone knows him. And it's a gift. It's not a unique idea. I admit, it's not a unique idea. It's been done before. So I can't take credit for the idea. It's a secondhand idea. But nonetheless, it's on the way, Charlie. But camels just aren't what they used to be. Every time I go to the place, I'm telling you, I get ripped off. I get slow camels. They bite and they spit. I mean, besides monkeys are the two animals I like the least. So it's on the way, Charlie, and happy birthday. Now, I work on isotopes, and I do two things in this regard. One is what I did in my first job here, in my first part of my job, is I was hired as a cosmochemist. What do you do as a cosmochemist? Urey invented this field, and it started in the 40s. You understand the origin, distribution of the elements, which is where I came at this, which is from stellar nucleosynthesis, through the planets and distribution all the way through until the origin and evolution of life. And then once you have a planet, then the cosmochemists don't care and they turn it over to the other people. So that's what I was hired to do. And this is a picture of me in my early sampling days on the moon. So what we're trying to do is try to go from this phase here, which is what I'm talking about, is when it's still in a planetary pre-solar nebula and the sun is just turning on, doing photochemistry, making molecules, all the way through making planets into here where you get into a meteorite. A lot of what we do is meteorite work also. So at that stage, here's what it is. I worked at I came here from the Fermi Institute at the University of Chicago, and I worked with people there that studied oxygen isotopes in meteorites. And there's this funny isotope distribution that you see in meteorites. The theory for this oxygen isotope distribution, that this is supernova debris. This was the theory for 20 years, is that you had a supernova, explosive carbon burning, you give off pure oxygen-16, which is what's showing in this plot, and that triggers the formation of the solar system. And Al Kaminer and a lot of people had models for doing this. Aluminum-26 gave you the time scale for doing this, and it worked well. But it's all based on one theory, that the only way you can get this is a nuclear process. So the first experiment I did with my startup money of $250 here at UCSD, replacement for Hans Suess, who some of you know, and I took over the laboratory of Harold Urey, who some of you know also. And that's why I have this. It has hydrogen, deuterium, and tritium, which Urey was responsible for. And part of it is that we measure these things, but we do the basic physical chemistry. And my first experiment here found a new law in physical chemistry and isotope effects. And it turned out that it was really a mess in terms of the chemical dynamics, and have made a living with that and other things. But the most important part is that it's a weird thing. And that's what I'll mostly talk about, is the forensics. we go out and measure this, and part of the deal is we have to develop abilities to measure things in different things, and small and precise. So part of it is understanding new rules. So when I came here, I was in Mayer Hall. In fact, where's Bob Dines? I was going to say, I was in Mayer Hall when I first came here. Now I'm in Urey Hall, which is probably where I belong. But I flooded Bob Dines' laboratory, and a physicist kicked me out of Mayer Hall. And so I've been banished to Urey Hall ever since. And but it's okay, it's appropriate. Now, in keeping with the Israel theme, part of what we do is try to understand, I'm just going to show to make the case, in understanding these rules, what's in it. And part of it is just pure, honest to God, quantum mechanics. And I wrote a theoretical paper with a guy in the PNAS, with a guy, and so keeping on this theme of Israel, Rafi Levine, who's a quantum chemist in Hebrew University, trying to understand the dynamics of what happens in selection when you break a bond. Seems simple, but you have to take a molecule where you know.
This UCSD TV program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest programs.
I'd like to welcome you all to the first of the two climate change sessions. This one, it's all free form. In fact, I have no idea what the other people in my section are going to talk about, but we'll find out soon. The descriptor is drivers and mitigation, and I'm Ray Weiss. I'm a geochemist here at SIO. Who started working in the ocean and using chemical tracers to study ocean circulation, and gradually evolved into the atmosphere in kind of a Darwinian fashion, and that's most of what I do now. The other speakers here are geochemists as well. I'm going to go last. Mark Thiemens, who is a chemist, geochemist, and our Dean of Physical Sciences here at UCSD, will be the first speaker, and he will tell you what he's going to talk about.
Thank you, Ray, I guess. So I'll have to decide as I go along what I'm going to do. So I've got some slides in here. I'll stick on time. But I wanted to say happy birthday to Charlie. So what do you say? First of all, well, I was on a search committee that hired Charlie, and